Hello guys, I am back once again with another video, second part of Material Science GATE 2020 solution. So let's dive in. A ceramic material is periodically heated and cooled between 25 degrees Celsius and higher temperature TF. During the thermal cycling, the material remains dimensionally constant. The material can withstand a maximum compressive stress of 200 MPa without failure. Material's coefficient of thermal expansion is given as this value, and modulus of elasticity is given as 200 GPa. So the lowest value of TF at which material will fail. Suppose one sample is there. If you heat, it will either contract or it will try to expand. So due to repeated contraction and repetition, one stress that is called thermal stress is developed inside the material. So that thermal stress sigma can be related with elastic modulus and change in temperature, as sigma is equal to E alpha delta T. So let's see what are the data it has been given. So cooled between 25 and higher temperature. So lower temperature is 25 degree T1, 25 degrees Celsius, and higher one is T2, that is unknown, and the material can withstand a maximum compressive stress. The thermal stress is given as 200 MPa without failure. So material's coefficient of thermal expansion, that is alpha is given as 7.5 into 10 to the minus 6 per degree Celsius, and modulus of elasticity is given as 200 GPa. So the lowest TF at which material will fail. So that is the value of TF they are asking. So we know the result. The thermal stress can be written as sigma is equal to E alpha delta T, and E is given as 200. Let's convert both into megapascal. So E will be 200 into 10 power 3 megapascal. So 200 into 10 power 3 into alpha is given as 7.5 into 10 power minus 6 into delta T, that is always delta of any quantity will always be final minus initial. Okay, so similarly delta T will be TF minus T1. So delta T is E alpha is 7.5 into, and delta T, that is TF minus T1, and sigma is already given as 200 MPa. So by calculation we can easily find out. I have calculated the value. The value is basically, if you calculate, T1 is already given as 25 degrees Celsius, so it's on you. Okay, you can convert it in Kelvin also. So since the value is given in per degree Celsius, so you should put always in degrees Celsius. Okay, so T1 is given as 25 degrees Celsius and the remaining same. So you can calculate. I have already calculated. The value will be 158.33 degrees Celsius. Okay, so this is the answer for this question. Another question is based on critical nuclei radius. Okay, that is R star. So during homogeneous solidification of liquid metal, the radius of critical nucleus, that is R star, in nanometer. So R star is being asked in nanometer. The given data is at temperature Ts. The given data is given sigma SL, gamma SL, that is solid liquid interfacial energy. So gamma SL is given as 0.18 joule per meter square, and the change in volume free energy delta GV is given as 0.18 into 10 power 9. So So you can watch my solid state phase transformation topic. I'll make the video on this topic. Actually, I'll make video on each and every topic of the syllabus of material science, so no worries, you can check there also. So here we know the formula for critical radius of critical nuclear radius, that is -2 gamma by delta GV. Minus is just for the meaning that delta G should always be negative, so that R star will come in positive. So there is no significance of negative sign in calculation part. Okay, since delta GV is already given in positive, or you can put the sign also. In the last we have to take the absolute value. So just take it minus. You can leave that also. 2 into gamma is 0.18 by delta GV is 0.18 into 10 to the power 9. So 0.18 will be cancelled out. So -2 into 10 to the power -9, since they are in meter. Okay, so answer will be in meter, and it is asking in nanometer. So it will be -2 nanometer. No distance will be negative. So we just take it as a absolute value, that is 2 nanometer. So answer is 2. This question is asked about powder processing or powder metallurgy. So in powder metallurgy, the statement 1 and statement 2 is given as sintering in vacuum leads to improved densification as compared to sintering under ambient condition. So it is saying that if you put some powder, that is not powder, dense powder, compacted powder. Okay, so some will be mixture of powder. First step, then we have to compact it, that is compaction. After that we go to the sintering portion, that is firing. So in sintering, what we do, we heat it below melting temperature, so the bonding between powders increases and the material gets densed. So it is saying that if you sinter it at normal atmospheric pressure, or if you sinter it at vacuum, so in vacuum comparatively the vacuum leads to improved densification. Density of sample will be more in vacuum situation. Yes, it is, because if you put the sample inside vacuum chamber, so all the trapped gases will be evacuated outside of the chamber. So if there will not be any trapped gas, there will not be any pores, and if there will not be any pores, the density will be more. So yes, first statement is true. So another statement is about closed pores formed during sintering inhibit full densification. So it is telling that if you have compacted sintered sample, and if some pores are trapped inside the sample, so it is saying that it generally inhibit full densification, means the density with pores is lower than the density of sample without pores. So yes, it is, because density is simply mass by volume, right? We are increasing the value by introducing pore, but we are not increasing the mass. The mass is constant, and if we increasing the volume, the density will be decreasing itself. So basically these pores or empty places. Okay, so the closed pores formed during sintering inhibit full densification. So it is also true. So both statement 1 and statement 2 are true. So option B is correct. So next question is from synthesis of materials. Synthesis of materials. So in one side it is given different process used in synthesis of materials, and another is the product of materials obtained, or final product. So you can go through the process also, what is powder processing, what is spin coating, what is isochromatic method, and what is chemical vapor deposition. So in powder processing, we take powder, we compact it, and after firing we compact it, and after firing and densification, that is also known as sintering. Okay, we just take it as a final product. Okay, so after sintering also, since we are using powders and we are compacting it, so we can get some porous product also from powder processing or powder metallurgy. Okay, and spin coating is something like that. I think I have one image for it. Yes, here it is. Spin coating is something we put some resin, okay, or organic semiconductor, anything we put here. After putting, we start rotate it. Okay, we start step 2 is starting rotating with this axis, rotational axis. After rotating, this raw material or precursor is expanded towards its radius, and finally we get thin films. Okay, so basically with the help of spin coating, we synthesize thin films. And another point is schizochromatic method or geochromatic method or Caesar method. This is purely for semiconductor single crystal synthesis. Okay, so this is for single crystal silicon, and I will upload some videos on it. You can check from the playlist also. So what about CVD? CVD is something we take one gas chamber, there will be one substrate, and there will be some carrier gases, and we put the precursor, means the raw material which we want to be deposited here. Okay, this, suppose we want to deposit some organometallic precursor like polysilicon. Okay, we want to deposit polysilicon, so we use its vapor form. Precursor is carried by carriers, at the surface they reacted with the surface and with some process. Okay, I'm not going into the deep detail of process with the reaction, so that is why its name is chemical vapor deposition. We take the precursor or raw material as gaseous form, and then they are deposited, and chemical means after chemical reaction with the precursor with the substrate. So chemical vapor deposition is basically for polysilicon, powder processing for porous bronze bearings, spin coating for thin films, and Caesar method for single crystal silicon or single crystal semi-crystal. So you can check from here which is suitable. So this question is from XRD. So consider FCC structured metal with lattice parameter A. A is given as 3.5 angstrom. If the material is irradiated using X-rays of wavelength lambda, so lambda is given as 1.54056 angstrom. The Bragg angle 2 theta, and it is being asked to solve for 2 theta. Okay, we have to solve for 2 theta. So 2 theta corresponding to the fourth reflection. The reflection or HKL plane is for fourth reflection. So basically we can solve it by using Bragg's law. We know for first order reflection we always take first order reflection, that is 1, n is equal to 1, so n lambda is equal to n lambda is equal to 2d sin theta. So lambda is equal to 2. D is also written, since it is cubic crystal structure FCC, so D can be written as A by root h square plus k square plus l square and sin theta. So we know A, we know lambda, we can find out this theta, but problem is we don't have this HKL. Okay, so there is one hint, it is same for fourth reflection of FCC. So what does it mean? What is the reflection? So if we take XRD diffractometer data, so we get something like that. Okay, we get, if it is suppose we are taking diffractometer data of copper, so we get some peaks. These peaks are called reflection. This one is first reflection, and this one is second reflection. Similarly, this one is third, and so on. So first reflection, so there is one rule of indexing. Okay, so this order, in order of the first, second, third, we can write h square plus k square plus l square values of both FCC and BCC and simple cubic. So for simple cubic, h square, k square, l square values are basically all 1, 2, 3, 4, 5, 6, so on. And for FCC, for BCC, this h square plus k square plus l square values are 2, 4, 6. Yet remember, I am not writing the ratio. Okay, in some standard textbooks it is written as h square plus h square plus l square ratio. So BCC will also be, the ratio will be 1, 2, 3, 4, because if we take 2 as a common out. Okay, so the value is 2, 4, 6, 8, 10, and so on. For FCC, the first reflection is h square plus k square l square value will be 3, then 4, 3, 4, then 8, then 11, then 12, then 16, so on. So for first reflection, this one is first reflection. Okay, so and this 4 is for second reflection, this 8 is for third reflection, and so on. So first reflection, for first reflection, h square, k square, l square is 3. So for first reflection, h square plus k square plus l square is 3. For second reflection, h square plus k square plus l square is 4. For third reflection, the value is 11, and then 12, and then 16. So this is the value for h square plus k square plus l square. Okay, so how you can remember it? So I have one trick. Let me erase it, and just for a simple cubic it is 1, 2, 3, 4, 5. Okay, for BCC it is 2, 4, 6, 8, 10. For FCC, how you can remember it or memorize it? 3, 4, 8, 11, 12, 16. There is one what you say, pattern is here. Okay, there is one pattern. Here we are adding plus 1, here we are adding plus 4, then here we are adding 3, then again 1, then again 4, again 3. So what we are doing actually, we are repeatedly repeating 1, 4, 3, 1, 4, 3, 1, 4, 3, 1, 4, 3, so on. So you can remember by I love you. You have to just remember the first number, that is the h square plus k square plus l square value for FCC of first peak is 3. You remember this only. Okay, and you can write for any number of peaks. And there is another concept also for 3 for h square plus k square plus l square value of 3. What will be HKL? So it will be simply 1, 1, 1. So that if you add h square plus k square L square, you will get 3. And there is some extinction rule. Okay, so I'll explain it. Extinction rule. So I'll explain it later or in a separate video. You can check it in a playlist. So by using extinction rule, you can say which peak. Suppose I'm writing 220. So you can say whether this reflection is for it can be found in FCC metal or can be found in BCC metal or not. If I write 310, so you can by extension rule you can say whether this HKL plane or reflection can be found in FCC or BCC or not. There is one rule that is called extension rule. So I am not going to that much depth. I'll upload a separate video for that. Just you remember it. Okay, that for first peak, the h square plus k square plus l square value will be 3, then 4, then 8, then 11, then 12, then 16. So if you remember just one number, that is 3. So by using 143, by adding 143 repeatedly, you can write all of them. So if you remember 3, this is first reflection, h square plus k square plus l square value of first reflection. Okay, so you have to add 1. I love you 143, so you add 1, then you add 4, then you add 3, then again 1, then 4, then 3, again 1, 4, 3. Similarly you can go further also. Okay, so now we know here the reflections, the h square, k square, l square values of first reflection or second reflection or third reflection or fourth reflection. So in the question it is saying you have to find out 2 theta for fourth reflection, right? So for fourth reflection, 1, 2, 3, 4. For fourth reflection, h square plus k square plus l square value is 12. Okay, so now you can solve for it. Okay, so A is given as 3.5 angstrom and lambda is given as 1.54056 angstrom, and you have to find out 2 theta, where for fourth reflection you have to find out. So for fourth reflection we know h square plus k square plus l square value is 12. Okay, so lambda is equal to 2d sin theta according to Bragg's law. Here n is 1 for first order reflection. So remember, first order reflection means n is equal to 1, and first reflection means first peak. Okay, first peak means in diffractometer pattern the peak. So I am talking about this peak. Okay, first peak. So remember the difference. Okay, don't be confused. So you can put here lambda 1.54056 if it is in angstrom. So if lambda is in angstrom, d should also be in angstrom. So unit should be same, or you can convert in meter also, no problem. So I am putting here in angstrom, both sides in angstrom. 2a by root h square plus k square plus l square sin theta. Now you can find out easily the value of theta. You know the value of h square, k square, l square. You know the value of a. Okay, so you can find out what theta also. The only trick here is for fourth reflection. So it is not saying for HKL plane for HKL plane, which plane will be there for 12. So it will be 2 to the 4, 2 to the 4, 2 to the 4. Okay, 3 3s are 9, 3 3s are 9. Okay, so this is the plane for 2 to 2 plane. So it is not asking directly for the 2 to 2 plane. Okay, for 2 to 2 plane HKL will be 2 to 2. So we can put here 2 square plus 2 square plus 2 square 12. So the only trick is here it is asking for fourth reflection. So you have to find out what will be the corresponding HKL value for fourth reflection. So for corresponding value of HKL for fourth reflection, you know the trick, 143 or I love you. Okay, by the way you can find out. For simple cube it is 1 2 3, for BCC it is 2 4 6, for FCC it is 3 4 8 11 12 16 so on. The number of Schottky defects per mole of KCl at 300 degrees Celsius under equilibrium condition will be. So the number of Schottky defects per mole. So it is asking find out the number of Schottky defects. Remember, for 1 mole. Okay, for 1 mole it is asking for 1 mole or per mole at 300 degrees Celsius. Conditions are, the given data is activation energy, that is delta Q, is given as 250 kilojoule per mole. So remember it is in kilojoule. Okay, kilojoule. and the Avogadro number Na is given as 6.023 into 10 to the power 23 mole inverse or per mole. So, and the value of R is 8.314 Joule Kelvin inverse. So there is two tricks. First is the formula for Schottky defect. It follows the Arrhenius distribution, Arrhenius equation. So Ns is equal to N e to the power minus Q by 2 RT. So the students first mistake student made was 2. They just missed 2. They write Q by RT. And the another chances where they might make mistake was, we are going to see how to calculate this N. It is not giving the value of N. At the place of N, it is given Na. So what is Ns and what is N? First let's find out. Ns is number of Schottky defect per unit volume, and another one N is for total number of atomic sites. Okay, total number of atomic sites per unit volume. So if it is in per unit volume means students are habitual with per meter cube. Okay, so for finding out, so N will also be total number of atomic sites per meter cube, right? So for per meter cube, N can be calculated by Na rho idhar aa. So Na rho by A. So density should be given, atomic weight should be given, so that we can find out this N. But students confused last year by seeing this Na. They are saying that Na is given, so what? N is not given, how can we calculate? So basically this N is for per meter cube. Okay, so you don't need to calculate this N. You can use just Na at the place of N also. Why? Because it is asking, Ns is asking in per mole, right? See, Ns is asking per mole. So the per unit volume is per mole. So this N will also be in per mole. Per unit volume means if Schottky defect is in per mole, so N will also be per mole. So what will be a total number of atomic sites per mole? That is Avogadro number of atomic sites or number of atom per mole, that is Na. So basically we have to put this Na at the place of N. That's it. Because Schottky defect is asked per mole and asked for per mole, and so you can put this N. So this N will also be the number of atomic sites per mole, and per mole how many number of atom will be there? That is Na, Avogadro number. So you just put this Na here, and you can easily find out the answer. So basically Na will be you just put it. Okay, so Ns you can find out. Na will be here, and you can put Na. Okay, so 6.023 into 10 power 23 into e to the power minus Q is given as 250 kilojoule. Okay, so 250 into 10 power 3 joule divided by R2RT. So 2 into R is given, and T is at 300 degrees Celsius. Okay, so T is 300 degrees Celsius means in Kelvin you have to always put. Okay, because R is in Kelvin. See, R is in Kelvin, so T should also be in Kelvin. So it will be 300 plus 273. So it will be 573. So you can put here 573. So you can find out the answer. Answer will come, I think, D. Let me see it. I have solved it. Yes, the answer will be D. So thanks for watching, and don't forget to subscribe. Okay, you know why.